Hello and welcome to week 7 of the Mastering Diffusion series. In this session, we will explore some of technical components of diffusion models. Specifically, we'll look into various conditioning methods used to guide diffusion models toward generating desired or high-quality samples. We'll also dive into diffusion distillation, a technique to accelerate the sampling process in diffusion models. My name is Jaeik Kim from ADAS Lab at Seoul National University, and if you have any questions, feel free to reach out to me via email address below. Let's get started. Today, as mentioned earlier, we'll be covering conditioning methods and diffusion distillation in more detail. Over the past 6 weeks, we have explored some of the most representative and foundational diffusion models and generative models. One prominent example was the variational autoencoder, VAE. We also look at diffusion models which are particularly characterized by two key processes. A forward process that gradually adds noise to the data, and a backward process that denoises, starting from pure noise to reconstruct the original data. However, the focus of the session so far has mainly been on generating random samples that resemble the training data. In practice, though, being able to generate samples that correspond to specific class or condition is far more important and useful. The first method I'd like to introduce is adaptive group normalization, which was used in the paper that later proposed classified guidance. In this approach, both the time step and the class embedding are projected and then injected into an ADA group normalization block, a type of residual block that many of you will be familiar with. More specifically, within the ADA-GN block, the following operation takes place. Given ys the projected time step embedding, and yb the projected class embedding, the output of the ADA-GN block is modulated linearly as follows. This formulation allows the model to adjust its activations in a conditioning-aware manner using both temporal and semantic information. As a result, we can observe a reduction in FID score compared to the DDP-M baseline shown in the second row of the table. This demonstrates that the use of ADA-GN effectively improves the quality of the generated samples. Next, let me introduce classifier guidance, also proposed in the same paper. To begin, let's first consider the unconditional denoising process where no conditioning information is provided. In this case, the denoising step can be expressed by the following equation. If we convert this term into a conditional denoising process, the expression becomes like this. Here, the denoising is explicitly guided by the class level y, allowing the model to generate samples conditioned on a specific target, and phi will be introduced later. This can summarize as a constant z, the original unconditional denoising process, and a term like p phi of y given xt. We will now derive this step by step. First, let's begin by assuming the forward process. Suppose the class condition noising process is denoted by Q hat. Now let's assume that Q hat, the class condition forward process, satisfies the following four properties. First, the marginal distribution over the original image is the same as in the unconditional case. So Q hat of x0 is equal to Q of x0. Second, the distribution over the label y given x0 is known since labels are provided in supervised settings. Third, the forward process is independent of y. Whether or not we condition on the class, the actual noise adding process remains the same as in the unconditional case. So q hat of xt plus 1 given xt and y is equal to q of xt plus 1 given xt. This is valid because the diffusion forward process simply adds noise and is not affected by y. Finally, by applying the Markov property, we can naturally accept the last assumption. And finally, these assumptions set the state for the derivation we're about to begin. Let's first use the third property to derive a useful identity. Let's consider the following expression. This expression can be rewritten as an integral over y due to the property of marginalization. This expression, by applying Bayes' rules, becomes like this. By applying the assumptions we discussed earlier, this integral expression can be simplified into the following form shown on the second line. Additionally, the first term inside the integral is independent of y, so it can be treated as a constant and pulled out of the integral. And since integrating the distribution of y over all possible labels for a given image yields 1, the expression simplifies as follows. For reference, this expression becomes equivalent to the following one based on our earlier assumptions. The key point to note here is the following two equations, which together imply that the noise process Q hat is exactly the same as the unconditional forward process Q. Furthermore, this leads to an important conclusion. In conditional diffusion, we can simply apply the same four steps as in the unconditional case. Similarly, the joint distribution of the fourth step is as follows, and this can be derived through a similar procedure, which we will omit in this session. Let me explain the second important property. Specifically, the classification distribution does not depend on xt plus 1. This starts from the application of the following Bayes rule. This can be simplified as follows by leveraging the property we examined earlier. By cancelling out common terms, it simplifies as follows. Now let's take a look at the conditional reverse process. Based on our forward process, the reverse process takes on the following form. By applying Bayes' rule a second time carefully, this equation becomes like this. By applying Bayes' rule once more, we can further simplify the expression as follows. Then, by applying the second property we discussed earlier, namely that the classification distribution does not depend on xt plus 1, we obtain the following term. Finally, the expression at the bottom becomes equivalent to the unconditional forward distribution. Due to time constraints, I recommend referring directly to the paper for this part. The proof is quite straightforward. Moreover, since we are currently interested in the distribution over xt, the classification distribution involving xt plus 1 becomes a constant and can be replaced with z, constant z, allowing us to pull it out of the expression. Now let's proceed to parameterize this expression. As we typically do, we use a denoising parametric model denoted by theta for the reverse process. Additionally, to handle the final term, we incorporate a classifier pi. Okay, so recall that the reverse process in diffusion is Gaussian. By exact formula for the log likelihood of a multivariative Gaussian, the term log phi theta of xt given xt plus 1 can be expanded as follows. Now let's further expand the classifier guidance objective, starting from the expression we have derived so far. Let's now apply the properties of logarithms and replace z with a constant c1, leading to the following equation. Next, we apply a first-order Taylor expansion to the log probability term in front of the constant c1, expanding it around the mean mu theta of xt. Then the gradient term can be replaced with the gradient vectors g, and the constants can be grouped into a new constant c2. And by applying a perfect square formula, we arrive at the following expression. So when we expand the equation more, we can group every constant into constant c3. This can again be rewritten using the properties of the multivariative Gaussian log likelihood, leading to the final expression. A log probability of xt sample from a Gaussian whose mean is shifted by sigma g from mu. What we can conclude from the above derivation is that conditional generation is essentially a mean shifted guided by the classifier's gradient. Illustrated graphically, this means that given an input at some point in the denoising process, we can compute the classifier's guidance at that input and use it to steer the image generation trajectory accordingly. Looking at the pseudocode, we can also see that a scaling factor S is applied, which practically controls the strength of the steering during generation. Classifier guidance can also be effectively applied within ODE-based trajectories such as TDIM. For detailed derivations, please refer to the original paper. Fundamentally, the key idea remains the same, leveraging the gradient of the classifier to guide the generation process. The paper also includes a quantitative comparison between unguided images on the left and classifier-guided images on the right. However, classifier guidance comes with several issues. First, it requires that a classifier be trained and available for every target class of interest. This limits flexibility and introduces overhead in practical applications. Second, this technique can be seen as an exploit of image quality metrics such as FID or IS score. That is, even if the generated images are not perceptually high quality to humans, they can deceive the classifier, artificially inflating evaluation scores. traditional classifier guidance uses the classifier guidance, a gradient directly in the following manner. This expression can be reformulated as follows. Because in the previous seminar session, we learned that the diffusion score function takes the following form. Please refer to the video at the top right. By contrast, the classifier-free guidance, instead of using a classifier, a single model is used to parameterize both the conditional and unconditional models. This can be expressed mathematically as follows. The condition C may or may not be given together with Z lambda. The model's epsilon predictions for these two cases are subtracted in a contrastive manner to produce a new class condition predicted epsilon tilde theta. The difference between classifier guidance and classifier-free guidance lies in the thickness of the box shown below. Notably, in the classifier-free guidance box, there is no classifier gradient term, which eliminates the vulnerability of classifier guidance to gradient-based attacks. Okay, so let's explore why this works well. First, consider an implicit classifier Pi. Since it is a classifier, when a latent Z lambda is given, it should be able to output the logits for C. By applying Bayes' rule, this can be expressed as a numerator and denominator form. Looking closely at the numerator, we can see that it corresponds to a conditional generative model since it generates Z based on C. Similarly, the denominator produces a distribution over Z lambda without the C term and can thus be regarded as an unconditional generative model. This means that by effectively leveraging these two generative models, we can construct an implicit classifier. Let us assume an oracle scenario in which we can obtain the exact score function epsilon star for both the conditional and unconditional distributions. Then the gradient of our implicit classifier can be expressed as the following term, which can in turn be derived from the properties of the diffusion score functions and the logarithms as discussed in the previous session. Using this gradient directly yields classifier guidance. And using this oracle noise prediction allows it to function as classifier-free guidance. This constitutes the theoretical background of classifier guidance. Of course, oracle level scores are unattainable in practice, but this still provides a certain degree of theoretical justification. If you look closely at the algorithm, you can see in the third line that during training, the class conditioning is adjusted with a certain probability. This is done so that during inference, as in line 3, the second model can be run both with and without conditioning, allowing the epsilon predictions to be subtracted effectively. By leveraging such classifier-free guidance, we can obtain higher quality images compared to diffusion backward processes without conditioning, as shown on the right. More recently, a variety of conditioning techniques have been introduced. A representative example is the cross-attention conditioning used in stable diffusion, where conditioning from various modalities is injected into the key value pairs to provide cross-attention based conditioning. Another conditioning technique is in context conditioning, which provides the condition by concatenating it to the part to be denoised. This approach is currently widely used in large diffusion language models such as LADA. Another example, distinct from label-based conditioning, is self-conditioning, which aims to improve the quality of the generated result. In this approach, the model uses its predicted original image or sequence as a condition for the next step's prediction, thereby enhancing generation quality. In the vision domain, self-conditioning has also been used to improve generation quality by further blurring patches based on the self-attention maps from the epsilon prediction process, and then iteratively refining the predictions. Now let's wrap up our discussion on conditioning and move on to diffusion distillation. First, what is diffusion distillation? In the practical use of diffusion, there has been one major issue, namely the sampling speed. For example, DDPM requires roughly 1,000 steps to generate a single image, while DDIM requires about 100 sampling steps to produce an image. This means that we need to call the model 100 to 1,000 times to generate a single image. Diffusion distillation addressed this issue by accelerating the generation speed. To understand it in detail, let's recap the probability flow ODE, PFODE, introduced in week 5. Deterministic diffusion sampling methods such as DDIM can be expressed as a PFODE with the equation given as follows. By integrating that DT, we can represent the sampling process as an ODE. This can be illustrated as follows. When a noise input is given, an image is generated deterministically by following a specific OD trajectory. This is precisely what the PFOD represents. In particular, the OD serving of DDIM, that is, its update rule was as follows. Here, a numerical analysis perspective comes into play. If the integration step n goes to infinity and our predictions satisfy mild smoothness conditions, the numerical error in the predicted image or sequence is known to converge to 0. This is also intuitively obvious. The following is an example from numerical analysis. If we increase the number of integration steps, we can continually approximate the exact solution more closely. And returning to the discussion of diffusion, the choice of OD solver has a significant impact on the number of sampling steps required. For example, traditional OD solvers such as Euler or Runge-Kungta cannot generate high-quality images within 100 steps, whereas an OD solver like DDIM can produce good quality images in 100 steps. Diffusion distillation leverages this idea with the goal of creating a student model, effectively an OD solver, that amortizes the integration step of the teacher model. This can be illustrated as follows. The student is repeatedly trained to amortize the teacher's two-step integration process, thereby reducing the number of sampling steps. In theory, this can be enable single-step denoising. However, diffusion distillation also has its own challenges. The prediction of the original model can be expressed by the following equation, where it generally predicts epsilon in order to estimate the original image x hat. Here, alpha plays an important role as it is the parameter responsible for the signal term in the log SNR. If alpha approaches 0, the output of our neural network will inevitably be increasingly amplified. This is not a significant problem in many-step diffusion, since the large number of steps can correct errors. In particular, alpha approaching 0 is more problematic in the early denoising steps, but in many step settings, these errors can be corrected over subsequent steps. However, suppose we distill the single-step diffusion model, then our model's predicted epsilon can no longer recover the original image, because with alpha 0, it must directly produce an estimate of x, which is mathematically impossible. To address this, the paper proposed various prediction schemes. The first is X prediction, which directly predicts X. The second approach is to jointly predict X and epsilon and then appropriately merge them to produce the predicted X hat. Lastly, this approach predicts the variable V, which the target image is obtained. A detailed explanation of V prediction is provided in the appendix of this paper. The laws also present an issue, and the original laws of our model is as follows. Similarly, when alpha is 0 in single-step case, the loss becomes 0, causing the loss to decrease for small steps and preventing the model from receiving sufficient training signals. To address this issue, this paper proposed two techniques: truncated SNR weighting, which uses the maximum of SNR term, and SNR plus 1 weighting, which adds 1 to the SNR term. The algorithm is as follows. As shown on the right, the sampling step of the student model are initially set to n, and the sampling steps are progressively reduced using the teacher model. Once the training of the student model is completed, the steps are again halved, and this process continues to further reduce the sampling steps. This paper successfully achieved one-step sampling. As shown in the following figure, even with a significant reduction in the number of steps, there's a little degradation in image quality. Quantitatively, it has been shown that diffusion distillation can generate higher quality images with shorter sampling steps compared to methods such as DDIM and stochastic sampling. The following is about consistency distillation. In fact, consistency distillation was introduced in consistency models paper, and some view it as a new type of model distinct from diffusion models. However, since consistency distillation fundamentally leverages diffusion models to accelerate sampling, we will include it here and briefly explain the concept of consistency models. A consistency model is defined by a consistency function which returns the original image x0 for all xt along the probability flow OD trajectories. This consistency function satisfies two properties. The first is self-consistency, which means that for any xt and for any two time step t and t prime, the model's prediction at these two time steps are identical. The second property is the boundary condition, which states that when the original image x0 is input to the consistency function, it returns the original image itself. From these two properties, it follows inductively and naturally that the consistency function is satisfied. In this paper, the consistency model f theta is defined as follows, with the key point being that C skip and C out takes value of 1 and 0 respectively. When the time t equals to 0, this ensures that the boundary condition is satisfied. This can be illustrated as follows. For any time step along the same OD trajectory, when it is fed into the consistency model, the model outputs the original image x0. It is important to note that this property holds when only the time step lies on the same OD trajectory. Now let us see how consistency distillation is actually performed. First, given the original image, we apply the diffusion forward process once to obtain the noisy image xt at time step t. Next, we perform a single integration step using a numerical ODE solver, such as Euler or Hund. The reason we obtain the image from the previous time steps starting from xt rather than running the forward process twice on the same image is that, as discussed earlier, one of the requirements for a consistency model is that the time steps in an image must lie on the same OD trajectory. We then fit the images from these two time steps into the consistency model. In consistency distillation, the model is initialized from a diffusion model and then trained accordingly. The consistency model then outputs its prediction for each time step. A loss function is then applied to minimize the distance between these two predictions, thereby enforcing the self-consistency property during the distillation process. Looking more closely at this loss, we find the term d, which serves as the distance metric function. This distance can be familiar L2 distance or a metric like LPIX, which measures feature similarity by passing the two images through a component like VGG. A target model is updated via exponential moving average, but due to time constraints, we will omit the details in this session. For a thorough explanation, please refer to the original paper. If you look closely at the algorithm, the red box at the top shows the process of using an OD solver to obtain the image from the previous time step. Based on this, the red box at the bottom measures the distance and updates the model in a way that accelerates it. As a result, consistency distillation CD enables one-step sampling and achieves better performance than PD, progressive distillation, as well as other model types such as flow-based models like rectified flow. That concludes today's seminar. So far, we have reviewed the mathematical background and technical components of diffusion. Moving forward, we will focus specifically on diffusion language models. In week 8 and 9, we will provide an overview of diffusion language models, and in week 10 and 11, we will examine their applications, for example, semi-AR methods and approaches for scaling diffusion language models. Thank you for joining today's long seminar. I look forward to seeing you next time. Thank you.